So let's communicate about the climate. I mean, let's climunicate.
Let's start with the first question. I'd just like to, very broad question about the gaps, how you see the gaps and uncertainties, as well as the things that we know about the climate. How do you see the situation from a broad sense in terms of climate change?
Yeah, I think the science questions are, first of all, how has the climate changed in the recent and distant past? That's an observational question. The second is, how is the climate going to change under natural and growing human influences? And the third is, what will be the impact of those changes on ecosystems and on society? Of course, the big question, which I hope we'll get into, is what should society do about all of that? But the science questions are really observational, modeling, and then the higher level ecosystem societal impacts. If I start with the observational side, I think what we're missing are long, detailed observations to quantify the natural variability. One of the things I like to point to is, as you probably know, there's almost 1,000-year record of the height of the Nile River as measured in Cairo. And that's a pretty interesting climate proxy because it drains about a third of Africa and quantifies the natural variability of the hydroclimate. And when you look at that, apart from large year-to-year variability, what is century-scale trends in the height of the Nile? And for example, from the mid-7th century to the mid-8th century, it was going down a lot when you look at the average. And that's a natural variability. And you have to understand that kind of natural variability before you can say, aha, it's CO2 in the modern record. So I think that's one. The second is we need better understanding observations of the oceans. The oceans are the long-term component of the climate system. They absorb most of the additional heat that's coming into the planet. And we have pretty poor long-term observations of the ocean, particularly at depth. That's starting to get better as we deploy floats and have other technologies to understand what's going on in the deep ocean. But it's got timescales of up to 1,000 years. And unless you understand that, again, it's tough to say that's CO2. So that's on the observational side. Of course, the projections rely on models, very big computer models. You probably know them as well as I do. But from the point of view of other modeling that one does in science and engineering, the models are in a pretty poor state. They don't get the temperature, the equilibrium temperature of the Earth right to within a couple degrees. They need to be adjusted or renormalized. We have a pretty poor understanding of the feedbacks in the models, particularly the clouds are problematic. The resolution is a problem. The current state of the art is probably about 100 kilometers on a side, and it's very difficult in terms of computer power to get down to resolutions that would be useful, let's say 10 kilometers or so in the atmosphere. So all of those things together say you should take what the models say with a grain of salt. If you look at the equilibrium climate sensitivity, which is a measure of how the climates respond to external influences, it varies by a factor of 2, 3. So we don't know more than, as Tim Palmer says, it's only a fuzzy picture at the global level and not at all fit for purpose at the regional or local levels. So I think those are some of the things we should all be, as scientists, working on, but also communicating clearly to non-scientists about what the certainties and uncertainties are.
That's great. I'm actually fascinated by what you've done, because coming from theoretical physics and learning all these things about the climate, it must have taken quite a lot of time.
Two things about that. One is, one of my elders, when I just gotten my PhD, said, a degree in theoretical physics is a license to poke your nose into anybody's business. And yes, as physicists, we have the tools, fundamental understanding, mathematics, clear thinking, and so on, to be able to jump into other fields. One does not do that lightly. I first got exposed to climate science in the early 90s and had the fortune to meet and learn from many of the senior figures in the field at that time in the course of doing studies for the government. But I would say I've been at it seriously for 15 years or so. And there's a lot to learn. And one is always learning and surprised.
of course, like we know, there's not a single person who can understand all the aspects, and so there's so much complexity. But you mentioned many interesting aspects. I'd like to try to unpack some of them. So when we look at the climate record, the first thing we know, we do normally is to look at the global variables. So the global temperature and the global emissions. It's good to have some records like the Nile and other places. The problem is that there are, even though they cover quite a large space, there are still parts of the picture. And to try to generalize from that sometimes is difficult. What is your view on that?
Yeah, look, globally is probably in some ways the least noisy record on multi-decadal scales. And we see, of course, the temperature globally, the global average temperature anomaly, if you want to be precise about it, has gone up by about 1.2, 1.3 degrees since 1900. But on shorter timescales, there are anomalies that we still don't understand fully. As you probably well know, the last couple years have seen a significant spike in the global temperature anomaly, and there's still a lot of debate about what has caused that, and in fact, whether the spike will go down or not again in the next year or so. I think it will, but causes include the cleaning up of aerosol emissions from marine transport. El Nino is just coming off. A lot of water vapor injected into the stratosphere from subsea volcano a couple of years ago. And we don't know. There's still a lot of debate about that. The fundamental problem is that human influences are a small physical perturbation, 2.5 watts per square meter on a radiation flow that's about 240 watts per square meter. So it's 1%. It's a chaotic system. It's poorly observed. And so it's a grand challenge to try to understand the response to human influence.
It is, yeah. Of course, there are many variables, but the fact that the temperature is increasing, the emissions, particularly CO2, is increasing, this is quite a strong correlation. And to explain it otherwise is also not easy. If one is to explain why it's going up, we should also explain why they wouldn't go up. The temperature wouldn't go up. But to your point about the 1%, actually, this is one of the parts that I saw in your book. You clarify that point, that if you take a 1% in radiative forcing, it's about 1% in temperature. So they actually line up if you want to look at that way.
Yeah.
But also, as we know, the CO2 has a disproportionate effect because of the spectrum. I also understand from listening to your interviews that you are also saying that CO2 is increasing and is driving temperature. So that's something that
of course, it's not the sole driver. There are other anthropogenic drivers, or there are natural drivers. But I like to talk about radiative forcing rather than CO2 for that reason, because aerosols are significant at the level of 1 watt uncertainty. But there are longer-term variabilities we don't understand. For example, the temperature anomaly went down a little bit from 1940 to 1970. It rose just about as much, not quite as much, but as strongly from 1900 to 1940 or so. And then we've got the longer-term warming from the Little Ice Age, from the 17th century. So there are things going on that are of a scale that says, gee, I'd really like to understand those before I say that all of the current warming is due to anthropogenic greenhouse gases.